Welcome to our talk today. We're here to present two new tools coming in LLVM 20 to help catch real-time safety issues. Before we get into all the fun stuff, let's get through the boring stuff. Who are we up here on the stage today? My name's Chris Apple. I'm a 10-year veteran of the audio industry. Currently, I'm a full-time cat trainer. I'm trying to teach my cat how to jump into my arms and not having much success, so maybe I need to go back to software engineering one of these days. And this is my illustrious co-host, David. He's also a long-term veteran of many different endeavors, and currently he's a software audio consultant. If you need any audio software consulting needs, please check him out and talk to him after the talk today. David and I have worked together for about a year at this point, and we haven't wrung each other's necks, so that's my glowing endorsement of him as a coworker. What have we worked on over the last year? Well, we are two of the three authors of RealtimeSanitizer, one of the tools we're going to be presenting here today. All right, what are we going to go over? I'm going to give you the very, very high-level overview of real-time programming as well as the existing strategies to detect real-time safety issues. We're going to talk about the two stars of the show, RealtimeSanitizer and the performance constraints attributes, and then we're going to spend the back half of the talk giving you a practical view comparing and contrasting these two tools. All right, let's get into a very, very high-level recap here. We don't have time to do a full primer on real-time programming. If you are brand new to this and this explanation is very unsatisfying to you, please check out any number of these talks. And of course, any good ADC has about half the talks on real-time programming, so I hope you drank in some of that this week. All right, as a reminder, real-time programming. Real-time programs must provide the right answer in the right amount of time. All computing strives to be correct, but real-time programming are defined by deadlines and the consequences that happen if you don't give an answer back in the right amount of time. In audio, the consequence is a dropout. Now, even if you're not a software engineer, you have probably heard a dropout in action, something like an unexpected click or pop or white noise while you're listening to YouTube or Spotify on your phone. Now, when I was working at Dolby DJ, we installed our software into nightclubs that were playing at 130 decibels. So at that point, a click or a pop or white noise is more than an inconvenience. It's actually dangerous. You might blow out your expensive speaker. You might hurt a guest's eardrums. So we need to be asking ourselves when we're writing audio playback code, how can we write code that does not drop out? This comes down to deterministic execution time. What, of course, that means is we can't have non-deterministic execution time. When we're writing in real-time context, we have a big list of disallowed calls. Things like system calls, allocations, mutex locks, and unlocks are all disallowed. What binds these all together is that they can indefinitely block progress of our real-time thread, leading to dropouts. Said in another way, we need to make sure this code is non-blocking, that it's always moving forward. Remember this word, it will come back many times during this presentation. All right, so what does blocking code look like? What does real-time unsafe code look like? Sometimes it is super obvious. You might be pulled into a code review and you see something like this. Something's taking a lock, allocating memory, doing a system call. You would say immediately, call the real-time police. I want to make an arrest. We need to do this on another thread at the very least. Oftentimes, it's more hidden than this. That's basically as easy as it gets in that previous slide. How about this? What's going on under the hood here? Our input and output array allocating memory. How about post report? Is this being passed by std function? Does anybody remember when std function allocates or not? If I saw this in a code review, I'd say, maybe this is safe. I'm not really sure. And of course, third-party libraries. How do we make sure that third-party libraries are following the same rules that we are? So how can we be confident that our code is real-time safe before it gets to the customer? And that brings me to the existing strategies as they are today. Well, the existing strategies, there are many of them. Things like code review, we just did that a few slides ago. Profilers and debuggers, ktrace, dtrace, things like that. And of course, documentation. I've seen multiple audio code bases with a big all caps comment saying, do not, under any circumstances, call this in the real-time thread. And of course, I've seen that called in the real-time thread, so maybe that's not the best approach. So all that's to say is each of these kind of have their problems, and none of them really deal satisfactorily with pre-built dependencies in third-party libraries. So let's live in a utopia for a second. Let's imagine the perfect tool that could just tell us if our code was safe or not. So to define this tool, This tool would assess real-time safety, of course, that'd be the main goal, detecting a wide range of violations, mallocs, locks, system calls, even in third-party and pre-built dependencies. Pointing to any problematic code, it's not enough to just wave a hand and say this is unsafe, but we want to see a stack trace or a line number so we can fix it. And hopefully be able to fail a CI pipeline so we are notified way in advance that something is wrong before a customer blows out their expensive speakers. So luckily for us, this utopia is just on the horizon. That is why we have another 40 minutes of this talk. We are presenting 2 new tools that are coming in LLVM 20 to help the real-time programmer hunt down these issues. We have RealtimeSanitizer, which is the runtime approach that David and I have worked on, as well as performance constraints attributes, which attempts to do the same thing at compile time. The rest of this talk, we're going to be going through all the ins and outs of these so you hopefully leave the room with a practical vision of how you can use this in your code base today.
All right, thanks very much, Chris. Okay, so I think over the next, I think it's going to take about 10 minutes. I'm going to introduce RealtimeSanitizer, the first of these tools. And I'm going to try to do just 2 things, really. First, just give you a little idea of what it looks like, how to use it, what it can do. And then together we're going to try to build a little bit of a mental model for how it works under the hood. And that's so in your own work, you can go away and make your own decisions about what kinds of problems that you have it might help you with and what kinds of problems it won't be able to help you with. So yes, this is the one that Chris and I have been working on upstreaming into LLVM. But there was another very important contributor to this. So Ali, who's here today, helped us put together the prototype for this version, presented it last year. So a lot of the credit for this tool existing goes to Ali. So thank you very much, Ali. Right, sanitizers in general. As a show of hands in the room, please raise your hand if you have used a sanitizer before. Great, okay, the vast majority, right? Raise your hand again if it has helped you fix a bug. Right, great, okay, clearly indispensable tools, right? Very, very useful. Now, just very quickly, as for the benefit of anyone in the room or online who hasn't used one before, here's a little flavor of the kinds of things they can do. So I'm going to use address sanitizer as an example. So I'm putting some problematic code on the slide here. I'm constructing a vector with size 16, and then I'm trying to read 1 beyond its bounds. That's very much undefined behavior. And if we don't compile this with any sort of extra instrumentation layer, if we're lucky, we'll get a seg fault. If we're unlucky, worse things will happen. But if we activate the address sanitizer instrumentation with this very simple compiler and linker flag, then our runtime address sanitizer picks up this problem and it says, hang on one moment, we're trying to read outside the bounds of the heap that was allocated to us. And critically, it pointed us directly to the problem. It said, this happened in example.cpp, line 6, column 12, and that's super useful. We can just go in there straight away and fix our problem. Okay, so what about RealtimeSanitizer? There's some problematic code on this slide as well, right? I'm sure most people in the room can see it's problematic because we've got a memory allocation in something that looks like a real-time function. And that is, of course, only problematic if process is meant to be non-blocking. So using RealtimeSanitizer is almost as simple as using something like address sanitizer. You need to do one extra thing, and that is you need to tell Clang that it's meant to be a non-blocking function. Then, just like address sanitizer, if you compile and link with this simple compiler flag, RealtimeSanitizer picks up this issue, and it says, wait, you made an unsafe library call to malloc. And we get a nice stack trace as well. It says example.cpp, line 6, oh no, line 12, down here, okay. And we can see that it's doing a vector allocation, and we can jump in there and fix our problem. That's great. So just to really hammer this point home, there's only 2 steps needed. Attribute your real-time functions with Clang non-blocking, compile and link with fsanitize real-time, and you're good to go. So now let's get onto the interesting bit. So the algorithm behind RealtimeSanitizer is actually really remarkably simple. It comes from the interaction between 2 cooperating components. One half of it is a lightweight runtime library that gets linked into your final binary. I'm going to cover that in a second. I'm going to start with the other half, and that's a compilation step that does some signaling, and we'll look at that now. So let's say that this is the entry point for our real-time thread. This is our process callback. Now, in the LLVM toolchain, I'm sure many of you will be aware that right in the middle there is some kind of abstract, assembly-like intermediate representation that our code eventually ends up as. This is nice. This is a domain in which optimizations happen. If you've activated the RTSan instrumentation and you've attributed your function with Clang non-blocking, then what the sanitizer does is it injects two function calls here in the intermediate representation. At the entry point to the function, it signals to the sanitizer, hey, we are entering a real-time context. And right in the very last instruction, before we actually return, we inject a call to real-time exit. And that's saying we're leaving the real-time context. And all this means is everything between those two lines has to be non-blocking. So where do we actually do that state tracking? Well, that's implemented in our runtime library. This is just incrementing and decrementing integers to keep track of how deep in a stack you are. And now comes the really interesting bit, right? Fundamental to a lot of sanitizers is this concept of interception. And what interception is using some platform-specific trickery, we can effectively reroute any function call to something like malloc from anywhere in our process to our own implementation, something like this, right? And we can choose to behave normally in that function, right? If we're some like UI thread, we can say, okay, I'm just going to return the result of the real malloc and behave normally. But we can do some other cool stuff. We can check if we're in a real-time context or not. Because we're in the same runtime library, we can check this state. And we can say, you know, are we between these two function lines? Are we between enter and exit? Did something that is supposed to be non-blocking try to call malloc? And that's the key. Like if something that was supposed to be non-blocking tried to call malloc, that's a big problem. And so in that case, we print a stack trace and initiate termination of the process. All right. So we've seen the power of interception. It allows us to do a lot of things. We can detect any function call. We can assert we're not in a real-time context. We can choose to error or behave normally. So what do we intercept? Right? It's going to come as no surprise to you that because Real-Time Sanitizer is concerned with non-blocking algorithms, Real-Time Sanitizer aims to intercept anything that could block. So not just memory allocation, memory deallocation. We intercept that as well. We care about locking mutexes, unlocking mutexes, signaling to threads, waking them up if they're waiting on a condition variable, and so on. So here is an incomplete list of the kinds of functions that we intercept. We've got our memory ones, our threads, file systems. Something's definitely gone wrong if you're trying to do HTTP requests from your audio thread, but it's important that we catch it. So they're there. Those of you with a keen eye will notice something in common about pretty much all of these functions, particularly around where they're defined, where they live, and that is in the C runtime, in libc. And why is that? Why do we intercept those functions? Hopefully the answer becomes obvious when we look at this diagram of the physical layers through which something like a memory allocation starts in the user C++ application and eventually ends up in the kernel. So at the highest layer, there's like obviously many different ways in which we can end up allocating memory. Almost none of them can Real-Time Sanitizer know about in advance, right? So we can't really intercept at that level. In the C++ runtime, we know these functions exist, and we could intercept those, but why would we when there is a thinner point in the funnel where at the libc layer, there's only really a handful of functions that at least directly deal with allocating memory. And also, this is just the final stage before we cross that kernel boundary and make a blocking operation. So really, that's the perfect place for us to intercept. Since we presented this, the prototype for this last year, we've added a few nice usability features which come in handy in real code bases. I'm going to show 4 of them to you here. First one is user-defined blocking functions. So as an example, let's take something like your own spin mutex. I think Dave and Fabian presented one of these in the Real-Time 101 talk. We have a try-lock operation, which is written to be non-blocking, and you can now attribute that non-blocking and verify that. Same with unlock, but what about this lock method? This lock is going to be a blocking operation, and critically, it's going to be blocking entirely in user space, right? This is a loop, and so Real-Time Sanitizer can't know about that, but you can tell it that it exists. So you can attribute it with Clang blocking, and that's an instruction to Real-Time Sanitizer to raise an error if this function is called in a real-time context. You can choose whether to exit or continue on error. So the default is just to exit on the first error. You can also set this environment variable to tell Real-Time Sanitizer to just continue, and it will also deduplicate your errors for you. There are some nice end-of-run statistics that you can take a look at if you add to this environment variable. And finally, I'm just going to touch very, very quickly on the ability to disable Real-Time Sanitizer entirely and suppress errors from certain function calls. In your own defined scope, you can use this scope disabler here. That will turn it off. And you can also pass a text file full of functions to ignore errors from if you want. Chris is going to touch on this in much more detail in a later section of the talk. So, in summary, yep, very simple. Attribute your real-time functions with Clang non-blocking, compile and link with fsanitize real-time, and be warned when bad stuff happens in your real-time threads.
Excellent, thank you. So alongside Real-Time Sanitizer, the runtime approach is performance constraints attribute, which is the compile time approach. So before we get into this, very special thanks to Doug Wyatt, who is the author, inventor, mind behind performance constraints here. We're just presenting his work. At their core, the performance constraint attribute system is just compile time warnings. So how do you enable compile time warnings? Well, with compile time warning flags that are prefixed with this -w. So our new flags are function-effects and perf constraint implies no except. When you compile with these flags, there are functions that get special treatment. Any function that is attributed as non-allocating is now disallowed from allocating any memory. Any function attributed as non-blocking is disallowed from calling anything that might block the forward progress of the method. Now, you might have recognized this before. This is our friend from David's portion of the talk. Clang non-blocking is shared between both of these tools, and this is the first chance to kind of shout out that these two tools were designed to work together. They're designed to interop. We're kind of sister projects. So, yeah, non-blocking is shared between each of these tools. To see these things in action, just like Real-Time Sanitizer, there are two steps. Let's say you have a process block that you want to avoid allocations in. You define your method, you add the non-allocating attribute, and you get a helpful compiler warning saying the non-allocating function must not allocate or deallocate memory. As simple as that. Very similarly, non-blocking. You have a process block that you want to make sure you're not taking locks in, calling system calls, etc. You add the non-blocking attribute to this function, and you compile, and non-blocking function must not call non-blocking function std mutex lock. Everybody's favorite triple negative that I've not stumbled on at all during this presentation. I will go to my grave saying not non-blocking. Yep, okay. All right, so performance constraints attributes form a bit of a hierarchy where non-blocking implies non-allocating, and both of them will warn if the function is also not marked no except. Now, I think these are very logical rules, and let's get into examples as to why. Looking at the top part of this hierarchy, non-blocking implies non-allocating. What this means, of course, is if you mark your function as non-blocking and try to allocate memory in it, you get a warning just like before, saying a non-blocking function must not allocate or deallocate memory. As we know from David's portion in the intro, malloc is one of these things that can take an indeterminate amount of time, so it cannot be called from a non-blocking function. We look down this hierarchy, both of these attributes will warn if the function is also not marked no except. So in this case, we have foo, which is marked non-allocating. And we get a warning saying non-allocating functions should be declared no except. To throw an exception, you must allocate it on the heap, To allocate something on the heap, you're inherently non-allocating. Thank you, double negative. So these are very logical. So keep this in mind, this hierarchy here. Non-blocking implies non-allocating, and both will warn you if the function is also not marked no except. Non-blocking is the king of this hierarchy. We recommend you put this on your top layer audio callbacks to get the benefits of both performance constraints attributes as well as RTSan. So perhaps more interesting in the performance constraints attributes are the function call restrictions that it puts in place. As you may well know, normal unattributed functions can call whatever they want. They can call other non-attributed functions, they can call non-allocating functions, and they can call non-blocking functions. You've been writing normal functions your entire life up to this point. As you move to stricter constraints, you can only call your constraint or stricter. Again, this makes sense. It doesn't make sense to call a function that might allocate from an allocating situation. So when you are in a non-allocating function, you can only call non-allocating functions and non-blocking functions. Non-blocking, being the strictest guarantee, can only call other functions marked non-blocking. Seeing this in action, we have process here marked non-blocking, calling foo, which is unattributed, missing the non-blocking attribute. When we try to compile, we have everybody's favorite triple negative non-blocking function must not call non-blocking function foo. We can fix this. We can fix this by adding the attribute to foo, and the compiler is happy here. The non-blocking function can only call other functions marked as non-blocking. To see a couple iterations of this, process block that's marked non-blocking can call foo, which is marked non-blocking. A process block marked non-blocking cannot call a function marked non-allocating, because this is moving to a less strict constraint. And last but not least, process marked non-allocating can call foo, which is non-blocking, because this is moving to a more strict constraint. So just keep this in mind that functions can call their constraint or stricter. As David presented in his section of the talk, you can define your own blocking functions. So in this case, non-blocking cannot call a function marked blocking. So same example as before, we have a spin lock lock method. We simply add Clang blocking here. Perhaps this is more enforceable than the all caps comment that I alluded to before. And when we try to compile, it will say it must not call non-blocking function. Further, there's this note saying it doesn't permit inference of non-blocking because it is declared blocking. Now, the second part of that sentence I think makes sense on its face, but let's talk about inference. What does not permit inference mean? So at this point, you might be kind of reasoning about the virality of these attributes. You have to put this on the top layer callback. You have to put it on all the functions that it calls, all the functions that they call, and so on and so forth. If you have a 10,000 line code base, this is a laborious process. It's going to take a little while. But constraint inference is here to help. As long as a function is defined in the same translation unit as the non-blocking function it's used in, the compiler is smart and inspects the body of defined here, and even though it's unattributed, will compile this with no issues. If you change defined here to do something unsafe, let's say lock a mutex, we get the same warning as before with a helpful note saying it cannot be inferred non-blocking because it calls non-blocking function. Of course, there are some limitations here. It doesn't work across translation unit boundaries. So if you have a third-party library, something like this defined elsewhere function, and you try to compile, you get a helpful note saying it cannot be inferred non-blocking because the definition is not in this translation unit. All right, at this point, you might be wondering, how do I even use third-party libraries with the system? And the answer is redeclaration. So we have third-party h.h here, and we've redeclared defined elsewhere in our main.cpp where we're using it. And crucially, we have redeclared it and marked it as non-blocking, which is allowed. We can always move to a stricter constraint here. So in this example, we compile without warnings and everybody is happy. However, you have to pinky promise everybody on your team that you looked at the source code and you promise that defined elsewhere is safe. You have to email me too. You have to say, Chris, I looked at the source code and it's for sure non-blocking because there's a footgun here. If thirdparty.cpp, if this method actually does take a lock, this is going to compile without warnings even though it is incorrect. Now, this is a great chance to shout out how complementary these tools are. If you were running RTSan on this code, it would warn on this line itself. So again, these tools were designed to work together to help kind of fill out the gaps that they each have. All right, that was deep in the weeds of performance constraints. Let's get back to basics. There are two simple steps to using performance constraints attributes. The first is compiling with our new warning flags. When we do, any function marked non-blocking, which is what we recommend for your audio callbacks, gets some special treatment. There are warnings when you allocate and deallocate memory. There are warnings when you call a non-blocking function. And there's even warnings when you initialize static local variables, which the compiler can insert locks around. So this is performance constraints. Let's get on to comparing and contrasting and giving you some different views on each of these tools. But first, we want to have a little bit of an interlude, a warning of sorts. We have the big Creepsta font here, so everybody's sufficiently scared. Neither of these tools can fully 100% guarantee your code is real-time safe. Now, what does this mean? Why even have this talk? Why are we on this stage at all? What I mean is each of these have their blind spots, things that they can't catch, kind of holes in the net, as it were. So we can't guarantee your processor gives you all the time that you requested. We can't guarantee your code runs faster than the allotted time. We haven't implemented all of the libc wrapper functions, things like this. Perf constraints has some similar blind spots and has the new blind spot of these misdeclared functions, right? So all this is to say, without stewing on the details too much, neither of these tools can fully 100% guarantee real-time safety, but they were designed to make writing real-time code safer and easier than ever before. They're not a panacea. They're not going to fully certify your code, but they're going to make your life substantially easier. All right, interlude over. Let's get into the back half.
Thank you very much, Chris. So let's start by looking at how they're similar. So we've already seen that both are designed to detect real-time safety issues in your code. They share these attributes, Clang non-blocking and Clang blocking. And again, be warned, there is no true real-time safety guarantee. And that's really where the similarities end. These tools are really more different than they are similar. And so the rest of the section is really dedicated to exploring their differences. So Chris and I are going to trade off a bit more. I'm going to start with the runtime versus compile time nature of the tools. And hopefully it should be obvious to you now that RealtimeSanitizer is entirely a runtime tool and performance constraints is entirely a compile time tool. But what does this mean about the inferences you can make about the real-time safety of your code? So it might be tempting to think these things. It might be tempting to think that, if my code runs fine with RealtimeSanitizer enabled, that it's real-time safe, that it's compliant. It might also be tempting to think, if it compiles with performance constraints enabled, that it's compliant. But really, of course, there are caveats to this. What is it on the RealtimeSanitizer side? This is only true if you actually hit every path in your code. If we have a situation like this where you have some allocation happening, but only in very rare circumstances, then there's very little chance RealtimeSanitizer is going to pick up on that. So what's the recommendation here? The recommendation is good unit testing with RealtimeSanitizer enabled. Try to hit every path in your code. And we're going to see in a future section that the runtime cost of RealtimeSanitizer is actually very low. So we recommend doing your QA builds with this sanitizer enabled and testing with that as well. Okay, let's take a look at the performance constraint side of things. This statement on the right is only true if you actually pay attention to those warnings and do something about them, and if you do any redeclaration of third-party functions correctly. So recommendation here is promote those warnings to errors. That means you can't miss them. And audit third-party code with RealtimeSanitizer. And it's not going to be the first time you've heard advice like this. It's just general good engineering advice. Extensive unit testing, good QA testing with sanitizers enabled, promote warnings to errors. And on this auditing third-party code with RealtimeSanitizer, people are doing this already. If you're interested in this, Farhaz and Valentina are talking later this afternoon in Bristol 3 about their work, so highly recommend you go to that talk. Okay, let's move on to the next one.
All right, great. False negatives and false positives. Where do these tools kind of fall over in some cases? So we've seen some possible false negatives, that is missing something that might actually be in your code. This is RealtimeSanitizer in the rare condition allocation, or maybe you've stumbled on some interceptor that we haven't implemented yet. let's talk about performance constraints. So performance constraints takes the kind of pessimist view, the kind of guilty until proven innocent approach. And this is best illustrated with an example. So is std vector push back real-time safe? Is this code over here on the side real-time safe? The answer to the more experienced among us is it depends. What I didn't tell you is I called this code after calling this prepare to play method, where we reserved more than enough space in this vector to push back and clear it and push back and clear it. Everything's good. However, when we run this through the performance constraint system, it says the non-blocking function must not call non-blocking function std vector pushback. And this makes sense, right? We can't even redeclare this as non-blocking because what it does is I've inspected the body of pushback. There's an allocation in there. Allocations are not non-blocking compliant. It does no control flow analysis. It can't reason about that this code is actually safe in practice. However, RealtimeSanitizer, when you run it on this code, it is happy. There's no allocation hit during any run through this loop, and everything is good to go. So in the case of the pre-reserved pushback, performance constraints had a bit of a false positive. What it says is this method is not always free of non-blocking calls, so I'm going to be inherently skeptical of it. RTSan, on the other hand, correctly did not error, saying this method is compliant on all the paths that we hit. So, as David said in his section, this is very, very useful in probing third-party libraries in the STL to try to get an empirical sense of what is safe and what isn't. So to kind of boil this up to top-level concepts, perf constraints analysis is never going to miss a problem, right? But it might be a little bit overzealous in some cases, like pre-reserved pushback. RTSan is never going to falsely report something. If you have a malloc that's reported by it, it for sure happened in a non-blocking setting. But it might miss a problem, some rare condition allocation or some interceptor that we haven't missed yet. So just be aware of these issues when you run these tools.
All right. Let's look at the cost. RealtimeSanitizer has a small but non-zero runtime cost. We're going to take a look at that. Performance constraints, adding these attributes due to the nature of their virality, there is some engineering cost, and we'll take a quick look at that as well. So, RealtimeSanitizer. We saw earlier how the sanitizer changes your code for non-blocking functions. We inject function calls like this, real-time enter and real-time exit, and essentially what they do is just increment and decrement a thread local integer. So that's very, very lightweight. Not much to worry about, especially if you're only putting this on the top level callback. But what about the non-constrained case? Let's say we've got some UI code where you're happy to make small allocations every now and again. Something like this make unique is going to boil down to a malloc, right? And if you've got the sanitizer enabled, that's coming from in your process, so we're going to intercept that. We're going to check if it's in a real-time context or not within that interceptor. And we also have to do a couple of extra checks. We have to check that we're initialized properly. But that's pretty much it, right? All we're doing is a few additional function calls that just check some state in integers. So yeah, when the sanitizer is enabled, there's a minimal runtime cost. And just to be very clear, when you don't have the sanitizer enabled, there's, of course, no runtime cost. Right. Let's take a look at the code conversion cost for introducing these attributes into a large code base. Let's say this only applies to large code bases. So you've just downloaded LLVM 20, keen to give it a go, and you've attributed your top-level callback with non-blocking, and you try to compile. You get this warning that we've seen a few times before. And of course, that's because our function foo is not attributed, so we need to go find our function foo in our project and attribute that as well and try again. And if we've got warnings as errors, we're going to get another error that we need to fix. So we need to go find bar, try again, and oh dear, you're starting to see a pattern emerge here. And you might find yourself in this situation, asking yourself, is this my beautiful code base? And the answer is, don't worry. There is a way to do this incrementally. So all is good. Chris is going to show you how to do that in just 1 second. So while there is some upfront effort to converting an existing code base to using these new attributes. We want to say that we think it is absolutely 100% worth it. Like, we would love to see a future where these attributes form a really key part of real-time interfaces. Maybe even they might get standardized one day. That would be fantastic. And yes, of course, any new project that you have, there's no cost whatsoever. You can start using these attributes right away. All right.
All right, so let's talk about disabling each tool. Now, there are 2 ways to disable RealtimeSanitizer. I'll get to that in just a second, but let's start with the issue that caused David and David Byrne such consternation not 2 slides ago. So you crack open LLVM 20 and you want to convert your code base to it. How do you do this more incrementally in this case? So just like any compile time warning, you can disable with pragma push pop. And luckily for us, Doug Wyatt is a very smart guy and gave us this macro that does exactly that. Before the call, it pushes the warning, it says ignore this warning, and then brings it back afterwards. In this way, we've kind of applied this macro band-aid. We haven't fixed any problems, but we've kind of given ourselves the ability to slowly and painfully pull this band-aid off when we see fit, which is, I hear, how you're supposed to remove band-aids. What I really like about this macro is that it's named in all caps, non-blocking, unsafe. So hopefully every time through your block here, you get a little bit of psychic damage saying, no, I'll get to that next week, I promise. So keep this in mind. This is how you're going to disable performance constraints attributes. RTSan has 2 different ways to disable things. So if you're familiar with Fabian's talk from last year, sinning on the real-time thread, sometimes you want to take a mutex if your real-time guarantee is out the window. How could you do this? RealtimeSanitizer ships with this interface, so you include this interface header, and you can define this scope disabler object, which simply disables RTSan when it's constructed and re-enables it afterwards. And when you compile, so this will run with no issues. When you take this mutex, all reporting will be suppressed. Further, when you compile without the fsanitize real-time flag, this will compile to a no-ops. You are welcome to leave these in your code. It will not affect any of your production code. All right, your other option for disabling RTSan is a suppressions file. So a suppressions file is a way that you can disable reporting for all the other sanitizers as well. And what it is a simple text file that contains some special strings. Our special strings are call stack contains, which says, does any call stack of any issue contain the string lock error mutex? So that would get around this error at the top of the slide. Or you can pass in a function name matches, which says, are any of our intercepted functions, like the pthread mutex functions, we're going to suppress reporting of that. Now you pass in this file using our RTSan options environment variable, and this will run and be happy. Now, there are various pros and cons of this. As David alluded to, we've really designed RTSan to be as fast as possible so you can hopefully listen to audio while it's running. So this comes down to speed. Basically, scope disabler is very, very fast. It early outs before any stack work. There's no string comparing, things like that. And that descends all the way to call stack contains. You can imagine we have to do string comparing on every frame of every potential issue, and that's why we have the snail emoji on the screen. So our recommendations here. Use scope disabler whenever possible, especially if you're leaving these things in your code like constantly, all the time. Use function name matches if you can't edit the source, you're playing around at runtime and experimenting. And use in-call stack when you have no other options. It's a very big hammer, but it comes with a very big price tag as well.
All right, thank you. Okay, so we're on to the final bit, and that's how you can use each of these tools today. So you can use both of them today. That's the good news. You can either build LLVM 20 yourself, or you can pull a Docker image. So we just released this one here. That contains both RealtimeSanitizer and performance constraints attributes. This is built on the tip of main of LLVM last night. So that's a nice way to try it out. Well, Chris and I are realists, and we realize that IT departments around the world might not be all that thrilled about you just downloading a compiler off the internet and using it in their systems. So we've added this extra option for you with RealtimeSanitizer. You can use it in standalone mode with other compilers if you're willing to do a little bit of hacking, and that is what the rest of this section is dedicated to. So before I start, just to make you aware, all of the instructions for this are on our GitHub helper repo. So if you don't follow it all, don't worry. You can find out exactly how to do it just here. So what you're going to do is go to the helper repo and download our RTSan standalone header and conditionally define this macro to conditionally enable it. From there, you'll need to initialize RTSan early in your process before any non-blocking calls happen. And anywhere that you would have put the Clang non-blocking attribute, you can instantiate one of these RA, II objects here, scope, sanitize, real-time, and that will effectively do the same thing. You will also need to build and link the RTSan runtime on its own. But if you link that into your library, then you should get pretty much all the benefits. We've tested this with Apple Clang version 15, that works, and with GCC 14 on Linux. But if your compiler supports including headers and linking libraries, you should be good. So just as a reminder, here's where you can find out more information. Okay, I think it's about time we wrapped up the talk. We've actually made pretty good time. How do you use performance constraints attributes? Well, it's very straightforward. You attribute your real-time functions, compile with these warning flags, and be warned when you try to do bad stuff in your real-time functions. RealtimeSanitizer, again, very similar. Attribute your real-time functions, compile with a simple flag, and be warned when you try to do bad stuff in a real-time context. Just to reiterate that both of these tools were designed to complement and work with each other. They fill some of each other's gaps. So our recommendation is, use both and write better real-time code. Thanks to all these people for many reasons. Thanks to Doug for coming up with this tool. Thanks to Ali for helping us build the initial version. The LLVM team have been absolutely incredible with their reviews. Thanks to these folks for reviewing our slides, and thank you very much to you for listening. Any questions? Yeah.